So what are the motivations behind Apache Spark? Firstly, Hadoop was very successful. Hadoop's widely used in enterprises that have got a lot of resources. However, extending Hadoop is quite difficult, and Hadoop is also Java only. So although Spark is based on the JVM, it also supports interfaces to Python and Scala. Following on from looking at the inefficiencies in the Hadoop architecture, simplified data flow was one of the aims, and faster processing speed. Mostly the faster processing is achieved through the use of storing intermediate data in memory rather than writing everything to disk, and also by successive optimizers which try and avoid transferring data over the network when it's not necessary. So what we find here is that Spark uses delayed execution as one of its models. So basically you will develop a program as a certain number of steps, and Spark doesn't actually execute anything till it gets to a certain point, which we'll talk about later. When it gets to that point, it'll run the optimizer and transparently, and that will change the order possibly of the way some of the data is executed, reducing network transfers. So that is something we're going to meet very directly. Another improvement that the people behind Spark thought of was the resilient distributed data set. And this is based on the idea I've mentioned already about fault tolerance. So Spark expects things to go wrong. Data is distributed in a way which is resilient. And what that means is if you've got some very large amount of data, it's distributed over multiple machines. Some process is started. If that doesn't return within a suitable amount of time, it will be sent to additional workers to process, and all of this is of course transparent. So that is a core part of the data architecture, and we're going to see some more of that as we go forward. So what components are there in Spark? Well, we've got the basic Spark architecture at the lower level. Mostly its operation is transparent. We don't need to know what's going on there. Specific parts of the architecture that we use: Spark SQL. So this is like SQL except implemented over resilient distributed data sets, so RDDs. But we've got a familiar SQL-like interface with a number of restrictions. Streaming is beyond the scope of this module, but is to do with processing large quantities of data in near real time as it comes in. Machine learning, we'll do a little look at that, but basically we've got a number of basic machine learning algorithms implemented in Spark and available. We have a little look at that, but not huge because machine learning has been kidnapped by Osama. And there is a graph processing extension, which again is beyond the scope of this module. So what is in the computing model? What do we actually need to know? Well, generally, some of the methods, most of the methods may be defined as either transformations. So remember, we're going back to earlier weeks. We met ETL, extract, transform, load. We collect together those transformations, and when we get to a certain point where we want some output, there are methods which are actions. Once we come to execute an action, the transformations which have been stacked up are optimized transparently, and then we notice that things start to happen. The way we see this as application programmers is some steps in Spark seem extremely fast, And that's because Spark hasn't done anything. It's stored the fact that you want to do some transformation, but until you get to a certain function, and we'll go through what these are, it actually doesn't do anything. So when we hit an action stage where we're collecting results, for example, you'll notice that those functions seem to be very slow, and this model is a little bit confusing to work with because the transformations are just stored, and it's only at the point where we generate an action that we start to see some errors. So it might seem that you've done a step successfully and then an error comes up 3 or 4 lines of code later. As long as you understand the model, it's quite straightforward, but if you don't, then it can be a little bit confusing. So we've got simplified data flow, and we try to avoid materializing data after each trip round the loop. So there's an example of doing the k-means, which is a clustering algorithm. We read our data, map it around, we group things. Something that we don't want to do, but which is necessary, is shuffling things around the network. Finally, we reduce the computation to get our output. So we've got a couple of ways that we meet to do computation with Spark. Mostly what we'll be doing is using the REPL, read, eval, print loop. So we'll be using Jupyter notebooks. We process a line of code at a time, more or less, and we can get output from that. Once we've gone through and built a whole application, we will submit that as a as a Python program to the driver. So you take your completed application and submit that in batch mode. We'll be seeing more of this in week 11. So here, for example, we've got our client, we've got the master, there's the driver program, multiple executors, which I've mentioned already, multiple data nodes. This is happening transparently. So our application is essentially getting distributed and worked on across these nodes. More particularly, we've got, for instance, here's some small program here, and what this will do, generate a graph. So the graph is transparent, that is, we don't see the graph necessarily. When we get onto the debugging tools in week 11, you will see how that's broken down. There is a scheduler which looks at the different parts of the computation and plans for them. Something which tracks blocks, that is data segments moved around the network, and something particularly that we don't want, but which is inevitable when we've got data executed on multiple machines, is shuffling data between different nodes. So depending on how you've structured your computation, there may be more or less shuffles. Shuffles are a bad thing because network transmission is slow. So if we've got a cluster of multiple machines, ideally we'll keep all the data in memory if we can. If it's not memory, then we might put stuff on disk. However, when we want to relate, for instance, we've got some large data set and we want to sort through that, we are going to have to move data around the network. And those are shuffles which we'll be monitoring. So clearly the way you structure your code can avoid shuffles and can improve code speed up. So I've already mentioned data locality. We're trying to avoid network I/O, so all the workers should manage their own local data. We should be trying to store the data in cache if we can. If something isn't in the cache, then we'd store this in a filing system.